Hello folks! Alright, today I want to get into formal processes for describing programming languages. So the idea is that we need some way to describe a language that's totally unambiguous so that everybody who's using the language or working on tools for the language actually understands how it's supposed to work. So if I write, if I come up with a description of C, then in theory, the people who are creating debuggers for it, the people who are actually programming in it, the people who are writing manuals for it, the people who are writing compilers for it, everybody has the same understanding of what's supposed to happen, so that if I read a C program, I know what that program is supposed to do when it runs. I know how the compiler should interpret what that program does, or the debugger, or how the developer should expect it to run. Right? We want to make sure that everybody's on the same page. So we need some way of clearly describing a language. So that's kind of what I want to get into today, and then over the next couple of sessions we'll get into more and more details about how to make that happen. Alrighty. So we could just use natural language. So just use, whatever your favorite language is, English, French, Spanish, whatever. So you could go through and just try and describe how everything works. But of course it's really difficult to get a perfect description of all the intricacies of a programming language when you're just trying to describe it with plain text. Right? There's lots of nuances that can be lost. You wind up with these huge long blurbs that nobody's ever going to read, and people are going to misunderstand even if they do read it. So there are issues with doing just a regular old natural language description. You can go through and give examples in pseudocode, but there are so many different possible combinations and again subtleties that it would be difficult to put together a complete compendium of all the possible examples that illustrate everything, and pseudocode that's going to illustrate everything. And even if you did, then people are, again, still going to miss some of them. If you give somebody a 10,000 page book of, here's all the examples that describe how this language works, nobody's going to read them all and nobody's going to remember them all. And it's going to be very difficult to develop tools based on those. So the idea is we need something that gives us a better starting point for describing and understanding languages. So we need a good description mechanism. We want it to be precise, complete, unambiguous. We want to make sure that it captures all of the basic structural syntax rules and captures the meaning of the language, right? It captures the meaning of what the different constructs are supposed to do. How's this while loop supposed to work? What does, pass by reference actually mean in the context of this language? So in an ideal world, whatever we use as our description would also allow us to kind of automate the process of generating tools. Could I come up with a way that I give a description of the language and I have some other program that reads the description and can generate portions of the compiler or debugger for me based on that formal description? So that's kind of a sub-goal or a secondary goal of the process. First goal is just to make sure that we can actually get the description right so that everybody has the same understanding of every situation. So what we'll do is come up with grammars or notations to describe the language that we're interested in. So we will use just regular expressions, regular grammars, to go through and describe the tokens that make up a language, things like identifiers, and the different symbols that we're going to use, and the different keywords in the language. And so we'll have regular grammars for describing the tokens, the individual components of the language, the individual key symbols or sets of characters that have some kind of meaning in the language. We'll have context-free grammars serve as the basis for just the structural syntax. An if statement starts with the keyword if followed by a round bracket followed by blah. So we'll use context-free grammars to give that portion of the syntax description. And then we'll somehow augment those context-free grammars to give more information about meaning and more context-sensitive information. So things like, the data types on the left and right hand side of an assignment statement have to be compatible. If you use a variable, it has to be declared before use, that kind of thing. So we're going to have these kind of 3 layers that we consider in our grammars to describe a language. So usually what you'll find is that these formal grammars are used as the, if you like, official basis for the language. The formal grammar defines this is what the language means. Now, not everybody likes to read a formal grammar in order to learn a programming language. Right? It's not necessarily very human-friendly. So usually you also augment that with, the host of natural language descriptions, examples, pseudocode, pictures, etc. But these are, if you like, informal translations of the formal definition. So these are meant to help people understand the formal definition, but they are really just to augment it. And usually what you're going to find is that, people create the grammar for a language, and over the first few years discover that there's holes or mistakes in the grammar, and that winds up getting refined. And they also produce the human readable support for the language. And again, you often find that, especially in the first few years, there are places where the natural language descriptions or the examples don't match the grammar, and you wind up with corrections to those as well. So you get this kind of iterative process before you get a really good formal definition and supporting descriptions of a language. However, that's just the nature of the beast. It's so complex that it is difficult to get these things perfect in the first few passes. When you're working with languages, they do tend to evolve over the years. Right? With any programming language of choice, you'll see that it started out typically much simpler than it is a few iterations down the road, where over the years people realize the language would be better, quote unquote, if it had this additional feature or this additional syntax, or could support this, or implement things in this way instead of that way. So you will find that languages evolve over time, and usually there's a fair bit of care taken to make sure that the new definition is still backwards compatible with the old definitions, so that if you had source code written in the old versions of the language, it can still run on the new versions. Now, periodically a change will be made to a language that goes beyond that, where you say, you know what, this is a kind of a complete break from the old syntax for the language. Certain programs written in the old syntax will no longer run in our new, or with our new tools for the language. So there, you will find that there are points where the community using the language kind of agrees on the idea that, okay, it's time to, we need this new feature or this new functionality so badly that we're willing to accept the fact that old programs will no longer be compatible, will no longer be, or portions of them will no longer be fully supported. So that's certainly something you'll see in the evolution of languages. So what we wind up with are programming language, or languages rather, to describe languages, right? Our grammars are essentially a language of their own used to describe the programming language that we're interested in. And again, different kinds of grammar have different limitations in terms of what they're capable of expressing. So we'll leave the proofs and the gory details to 320. What we're interested in here is sort of the applied side, where we're going to go through, and as I mentioned earlier, we'll use regular grammars just to describe the basic tokens of a language, the basic symbols, what alphabet we're using, what the keywords are, what operators we're using, what symbols, what makes up a valid identifier, what makes up a valid integer, what makes up a valid real number. That kind of thing we can describe with our regular grammars and regular expressions. Then to describe how we put those things together to form an assignment statement, or to form an expression, or to form a while loop, or to form a function definition, we'll use context-free grammars to describe the structural rules for those. And then again, we'll augment those with extra information and extra rules to capture context-sensitive information. Things like the idea that a variable must be declared before it's used, to check scoping rules, to check data types, that kind of thing. Now, in terms of a compiler, what it will typically do is we'll design it to follow those grammar rules, and a compiler will typically make use of, either explicitly or implicitly, the different layers of grammar rules that we've built up. Right? So our compiler might do some pre-processing. It'll read in the source code for the program, strip out white space, strip out comments, that kind of thing, put it in some sort of standardized format, do any pre-processing that has to happen, right? Any hash defines, any macros, any templates, that kind of thing, and apply the regular grammar rules in some fashion to turn that sequence of characters into a sequence of tokens, the keywords, the identifiers, the operators, the symbols, etc. that we're using. So it's often called scanning or tokenizing. Once we've got that, we'll make use of those context-free grammar rules to build kind of a tree-like representation of the syntax, a tree-like representation of the program. Right? It's a program made up of a function definition and then 3 statements and then a function call or whatever it might be. So we'll apply the context-free grammar rules to build a representation of the syntax. Maybe we'll do something like create a symbol table that keeps track of all of the different symbols in use and key information about each of them, their scope, their type, that kind of thing. And then we'll use the grammar augmentation rules to expand our syntax tree, to expand this abstract representation to include context-sensitive information, to include the semantic meaning, if you like. Then it will go through and use that intermediate representation and generate the code in the target language. So for instance, if our compiler is trying to build to an executable, then it's going to go through and generate the machine code for the target platform based on that intermediate representation and how to turn that into code in the target language. So the compiler is typically making use of all those different layers of rules, of grammatical rules that we've put together. Now, similarly, if we've got a debugger or an interpreter, it's going to be doing similar sorts of things where it's reading the source code, putting it in standard forms, pre-processing, scanning, going through and parsing to put together the abstract representations. Right? It's going through and doing these similar steps. Now, if we've got a nice formal set of grammar rules for a language with the regular expressions and the context-free grammar and the augmentation rules, then maybe we can have tools that read that set of grammar rules and just spit out a compiler for us or an interpreter for us. So these are often called compilers, right, where they read the grammar rules, and of course those rules have to be written with a very specific syntax, and they generate the tools for us. So we'll take a look at tokenizers or scanners that use the regular grammars and produce a program that will read source code and generate a list of tokens. So there's programs like Lex and Flex that we'll be making use of and talking about that do this for us. We'll be using tools like Yak and Bison, yet another compiler, Antler's another one, where, again, these things read a set of formal grammar rules in a very particular syntax, and based on those rules, they spit out a compiler for us, or an interpreter for us, or a debugger for us that can read source code in the desired language and do something to it. Check it for errors or translate it into some other language. Usually these aren't as efficient as we could get a compiler or debugger if we wrote it carefully by hand, right? Because again, these are kind of abstract. They're meant to be able to handle any kind of grammar that's, that follows the syntax for our formal language descriptions. So they're not usually as customized as we could get by hand. But if we've got something that can just read the grammar and produce the tool for us. It makes it easier for us if we can just describe the grammar rules for a language and say, okay, you go give me the compiler. Even if it's not as efficient as one I would write by hand, it's going to be correct, and it's going to be a lot faster for me than me sitting down and writing it by hand and getting it correct. So these are all things that we'll consider in greater detail over the next few sessions.